consider this mechanical parts. Even if you design them well satisfying mechanical strength criteria, it may fail due to a phenomenon called fatigue. Historically, many design disasters have happened by neglecting effect of fatigue factor. To understand what is fatigue, let's consider this metal wire. You have to break it. So how will you break it? Will you pull it from both ends, or will you do this, where you bend the wire upward and downward repetitively? Your answer is obviously the second option, because this method requires less effort compared to the first case. This is a well-known example of fatigue failure. So how does material fail due to fatigue? To get answer for this question, let us have a close look at stress variation in wire cross-section. When you bend it downwards, bending stress is induced in the wire. It will be tension at top area, and compression at bottom area. When wire is at equilibrium, there will not be any stress on wire cross-section. When wire is bending upwards, there will be compression at top and tension at bottom. So if you trace stress induced at a point with respect to time, it will vary like this. As a fluctuating stress with time. Initially the point will have positive stress. After that zero. Then negative stress. The same cycle repeats again and again. Such fluctuating stress is the root cause of fatigue failure. When such fluctuating stress act on a material, it will initiate something called micro-crack. This crack will begin to grow with fluctuating load, and over time it will cause an abrupt failure. This is why failure due to fatigue is a dangerous affair. Unlike failure due to static load, fatigue failure happens without any warning, it doesn't even make a neck. And the failure is completely unpredictable. The same phenomenon can happen for axle of this motor, where it is undergoing fluctuating stress due to gravity effect of this mass. This rail wheel, when it is contact with the track, produces a high contact stress. But when the wheel rotates, stress gets relieved. When it comes back to original position, contact stress arises again. So this also is a case of fluctuating stress. It may fail due to fatigue, if we do not design it properly. Same is the case with gear pair. Here contact stress arises at mating point. Now, the most important part in fatigue analysis. Relationship between stress amplitude and number of cycles it can execute before it fails. What will happen as stress amplitude decreases? Yes, you are right. As stress amplitude decreases, number of cycles required for failure increases. Anyway, we will analyze this trend more systematically. We will draw number of cycles in x-axis, stress amplitude, and y-axis, both in logarithmic scale. Let's start with the maximum stress a material can withstand, its ultimate stress. So this will happen, as you increase the stress, even before completing one cycle, the material will get broken. So this will be the corresponding point in SN graph. If you decrease the stress amplitude, it will execute more number of cycles before it fails. Decreasing stress even further, it will be able to execute even more number of cycles. So this will follow a trend like this. But not forever. You can see after particular stress amplitude, even with slight decrease in stress, number of cycles required to make it fail increases drastically. Or in short, if you have stress amplitude below this limit, number of cycles to make it fail jumps to infinity. Or material never fails after this limit. This limit is known as endurance limit. Below endurance limit it is safe to operate the material. Engineers always try to design their components by keeping stress amplitude below endurance limit. You can see that endurance limit is way below ultimate stress value. It is a good approximation to consider these two regions as linear. but here we had a case of complete stress reversal, where stress mean value was 0. What will be the maximum stress limit for this case, where stress reversal does not happen? It has got a mean value and amplitude. For this purpose we have to use something called the Goodman diagram. In a Goodman diagram, mean value of stress is drawn on x-axis. Amplitude of stress is drawn on y-axis. When mean value is 0, we know safe stress limit is same as endurance limit. When amplitude of stress is 0, it is same as a static loading condition. So safe limit for tension is ultimate tensile stress at tension, and safe limit for compression is ultimate tensile stress for compression. According to Goodman analysis, safe stress amplitude limits for all other cases lie on straight lines connecting these points. So for a particular stress mean value, we can find what's the maximum allowable safe stress limit from this diagram. It will be here. Similar analysis can be done considering safe limit of amplitude 0 condition as yield strength of material. This is known as Soberberg diagram. Generally, Goodman analysis is the most preferred one. To learn more on fatigue failure, check the second video. Thank you.